That looks beautiful. Look at those graphics.
Spoiling what's coming up by having
oh, it's a teaser. Oh, that's great. Thank you.
The rest of the talk's all Greek letters after that, I'm afraid.
Excellent.
Clever to start with the graphics to catch the attention.
You'll be able to tell who made which invited talk slides just by a chroma analysis.
Now there's a great PhD topic. We should give it a couple more minutes here, if that's okay with you, Alistair.
Yeah, that's fine.
Terrific. Absolutely. Thank you. It's so strange not to have people running from other rooms or anything.
I know, yeah. Have you been enjoying the rest of the conference?
Wow, you know, it's so strange but wonderful. How about you? I
have been, yeah. I've dipped in and out of it, and the bits I've dipped into I've really enjoyed.
Yeah.
It's been, I feel slightly ashamed to say this, but I'm submitting a paper to PLDI. Well, I'm not ashamed about that, but I'm ashamed to say that the clash with the PLDI deadline has definitely detracted from my enjoyment of the conference.
Yeah.
Yeah.
Timing is everything, isn't it?
Yeah.
Well, it's really generous of you to take your time to give this talk today.
Oh, my pleasure. It's really nice to be invited, and yeah. And I've enjoyed the whole day.
So we do have a very action-packed last session here, where we get to have this incredible talk from Alistair. We get to see some sneak preview of these slides. And then, you know, this is the roundup after this, which is absolutely amazing. All the people that dedicated their time today to help out students with these questions, and certainly to have this coming together of eCoop and Splash. What a great, I think, a really great opportunity for us to get everybody together like this. And that roundup it's a lot of people, but and it's going to be pretty quick, but it'll be hopefully sort of the takeaway thoughts from our academic panel at the end here. So I think do you think, should we give it a little bit more time, Alistair?
I'm happy either way. Yeah, we can give it a couple more minutes.
Let's do it. Okay. Well, since it's not as though people have to, fight for seats or anything today, if you're comfortable with getting us started, Alistair, that would be great. Thank you very much again for doing this talk. Really looking forward to this. And again, wow, look at those pictures.
Cool. Okay. Well, thank you very much for the invitation to speak at the doctoral symposium, and thanks very much to all the students who submitted your fine work to the symposium. Hope you've had a good day. I'm Alistair Donaldson. I'm a professor of computing at Imperial College London, and I'm also a software engineer at Google. And I'm going to talk to you about a project called GraphicsFuzz, which is about metamorphic testing of graphics drivers, and we're in particular applying it to Android graphics drivers at Google. So in this talk, I would like to do two things. One, to tell you a bit about the technology behind GraphicsFuzz, and two, to tell you a little bit about how GraphicsFuzz went from being an academic research project to a startup company that then Google acquired. And I would love to answer questions during the talk as well as after. So if you have any questions during, please feel free to interrupt. Do interrupt me mid-flow. It's much harder in these Zoom talks to know when it's appropriate to ask a question. So I want to tell you now, anytime is appropriate. And of course, I'm happy to take more questions at the end. So suppose that you were a graphics developer and you wrote a little program to render an image like this. And you ran it on your graphics driver, and instead you got an image like this one here. So looks kind of cool still, but it's not the image you wanted. That would not be good. Maybe you had a graphics program to render a galaxy like this, but instead your machine blue screened. That wouldn't be good. And perhaps worse still, suppose you had another nice image you wanted to render, and you were doing this in a web browser using WebGL, which is a technology for letting you do graphics rendering from JavaScript. If instead someone visiting your page could instead get this be rendered from another one of their tabs, then that would be very serious, right? Because you could make your web page malicious and you could capture data that was being rendered supposedly to another one of their browser tabs, but that was actually being captured by your web page. So these are all examples of some bugs we found using the GraphicsFuzz project, where a graphics compiler has a bug that leads to either an image being rendered wrongly or leads to the graphics driver getting into some kind of bad internal state that can bring down a whole system, or leads to the graphics driver leaking graphical data to the wrong place, which is a potential security exploit. And actually my PhD student, Paul, got a Chrome bug bounty for this particular exploit shown here. So what I'm going to tell you about is our technique called GraphicsFuzz, which finds bugs in graphics drivers using a method called metamorphic testing. And in particular, it finds bugs in the compiler components of graphics drivers. All graphics drivers contain one or more shader compilers, which are responsible for compiling programs called shaders that are designed to run on graphics processing units. So to give you a bit of terminology that I'll be using in the talk, there are a couple of ways of doing graphics programming, and two popular methods are using the OpenGL-ES API and the Vulkan API. And what these APIs do is they orchestrate a bunch of operations on your GPU device, and the programmable aspect of the GPU is controlled by shader programs. They run across the many cores of the GPU hardware and either cause things to be rendered to the screen or cause computations to be done between buffers. So if you're familiar with CUDA or OpenCL, then a shader is kind of like a kernel in those programming models. And the OpenGL programming model has a shading language called GLSL, the OpenGL shading language, and Vulkan has a shading language called SpearV, which is an intermediate representation. Okay, so what we are doing in this work is automatically testing shader compilers, and we're doing it using a technique called metamorphic testing. And I want to explain how metamorphic testing works for testing any old compiler, not necessarily a graphics compiler. Suppose you've got some program P, and let's imagine that P is a well-defined deterministic program, so that when you run P on an input, you'll get a well-defined output. Well, if we compile the program P into an executable E, and then run that executable using an input I, then we'll get some output, which we can assume is well-defined. We don't know a priori what the output O is going to be, but we know that there will be some well-defined output. If we can then apply transformations to the program P that preserve its semantics to get a program P prime, so maybe refactorings or optimizations or obfuscations, then if we compile P prime to an executable, then the executable will be very different from E in its object code because we've compiled a different program. But because the programs are semantically equivalent, if we run both E and E prime on the same input, then we should get the same output. And if we don't get the same output, then there's a bug in the compiler. So if you know about metamorphic testing, we've got a metamorphic relation here that says when we compile and execute P, we get the same result as when we compile and execute P prime, as long as we use the same input. So this gives us a way to solve the oracle problem for compilers, where we don't know when we have a program and an input to that program. We don't have a reliable way of knowing in advance what the correct output for that program and input is. Having an oracle for that output is essentially as hard as building a compiler, which is the thing we're trying to test here. So we get around the oracle problem by actually comparing the results that we get from compiling and executing multiple distinct programs. And if we get different results, then we know that the compiler can't be correct. We still don't need to know what the result should be. We just know that these programs should give the same result. And if they don't, then there's a compiler bug. Before I move on, does anyone have any questions about that? Does that make sense as a concept? Okay, I'll take your silence as assent. So this technique, metamorphic testing, has been used in many domains, but the first instance I saw of metamorphic compiler testing is from a really nice paper from PLDI 2014 from researchers at that time based at UC Davis called Equivalence Modulo Inputs. And this is an instantiation of what I showed you on the previous slide. What they did, which I think was very clever, was we'd take a program P and compile it, and then they would profile the program on a specific input. And that profiling would give a partitioning of the program statements into the statements that are covered by the input. Let's call those, well, we'll give those a name. There are some statements that are covered by the input and some statements that are not covered by the input. And we'll call these statements that are not covered by the input D for dead. So these statements of the program, they might not be dead code in general, but they're dead with respect to the input I. So now what the researchers did is from a program, P, they would manufacture a whole load of programs, P1, P2, P3, etc., that differ only in these statements D. And what they did in their original paper was actually just randomly deleted statements from the dead portion D. And although these programs globally might behave very differently, on the input I, they should behave in precisely the same manner, assuming that P doesn't trigger undefined behavior on I. So if we compile all of those programs with a single compiler and execute them all, then if we get our result, this 42 here, that differs from the other results, then we know there must be a bug in the compiler. And very likely this program P2 is the one that's miscompiled. Of course, in theory, it could be the only one that gave the correct result, but that's very unlikely in practice. But the point is, a result mismatch points to a compiler bug. And this method was really successful in finding a whole lot of bugs in the GCC and LLVM compilers, and various evolutions of the method have been successful since. In fact, the researchers were acknowledged in the LLVM4 release for their bug finding effort. Okay, so what we're doing in the GraphicsFuzz approach is inspired by this work. We've gone a bit further, and rather than doing profiling and finding code that can't be reached by a certain input, we've devised a whole load of transformations on the graphics shading language, OpenGL, or GLSL is the name of the shading language. We take an original shader and convert it into equivalent form. So we take an original shader program, we push it through the graphics stack to get an image, and then we apply a whole load of semantics preserving transformations that we've implemented in a compiler framework to get a stack of variant shaders. And each one of these variant shaders should render the same image as the original shader when we push it through the graphics stack. So if they all give the same image, which they should do, then that's fine. We haven't found any kind of bug. But if we get a different image from one of the variants, or if we get a crash, then we found a bug in the graphics driver. Now, I should clarify a little bit here that graphics hardware uses a lot of floating point operations, and floating point operations are sensitive to round-off error. And graphics programming languages are very relaxed with respect to what compilers are allowed to do with floating point values. So actually, the point here is that if we see a radically different image from one of our variant programs, that indicates we found a compiler bug. If we see an image that differs in just a few pixels, we can't say conclusively whether that's acceptable or a compiler bug because the language is vague with respect to floating point. So in our work, I'm not going to go into the details of it here, but we have some methods for estimating when we think an image is wrong enough that it probably stems from a bug in the compiler rather than from legitimate rearrangement of floating point operations that can lead to some small differences in an image. Okay, so this is how GraphicsFuzz finds a bug. Like I said, it's inspired by this EMI technique from PLDI 2014. But the transformations we've implemented are quite specific to the graphics programming model. Is it useful though? So if I find a bug with GraphicsFuzz and get some crazily transformed shader program like this, and I say to a GPU compiler maker, there's a bug in your compiler, trust me, there is. This crazy program should produce exactly the same results as the original program. Good luck detecting it. Well, no, that's not going to be very useful. First of all, it may not really be very actionable to be given a small program and a massively bloated transformed program. Even if the transformed program should be equivalent to the original program, how as a compiler developer are you going to start working out what is actually wrong? Second, GraphicsFuzz is itself a complicated tool that will be prone to bugs just in the way that a compiler is prone to bugs. So there may be bugs in GraphicsFuzz, and this bloated program may not truly be equivalent to the original. So it could be a big waste of a developer's time to go and investigate this bug that I claim to have found. So to counter that, we use test case reduction. We've got our original shader, and we've got our bug triggering shader that was manufactured by applying a whole load of these transformations. And because we applied the transformations with our tool also knows how to reverse the transformations. So what test case reduction does is it keeps trying to reverse some transformations, each time checking whether the resulting shader program still triggers the bug that we found. So it gives the same crash, or it still triggers a bad image, an image that's substantially different from the image rendered by the original shader. And we do this until we find we can't remove any single transformation without the bug disappearing. And what this gives is a small bug triggering shader that differs only slightly from the original, that still triggers the bug. And the pair of the original shader and the minimally different shader are a really good starting point for compiler developers to go about diagnosing and fixing the bug. And we've reported many, many bugs over the last few years to developers. And this small diff format has proved to be very successful for them being able to act on the bug reports. Here's an example of a wrong image compiler bug that we found near the start of the project. And the diff is shown on the right-hand side. So there was a piece of code that returned the result of a call to default color. And what our tool did is many things, but after reduction, after reversing the many things it did to find a minimal difference, we found that wrapping this return statement in a switch on the value 0, with one case saying if 0 is 0, then return default color. This transformation, which is evidently semantics preserving, was enough to trigger the bug. So often the differences that we get after we apply fuzzing and then apply test case reduction are very small and very actionable. Here's an example of a crash compiler bug that was found in a vendor driver. So when GraphicsFuzz finds a bug that leads to a shader compiler crashing, it can be much more aggressive in its reduction. It doesn't need to preserve equivalence with the original program. It can just shrink down the program as much as it possibly can to try and find the smallest example that triggers a bug. Here's a slightly more interesting and more recent example. The details of the program don't matter, but the point is you can see on the left-hand side a small bit of OpenGL shading language code And this triggered an assertion failure in LLVM's AP float module for arbitrary precision floating point arithmetic. Okay, so that's an overview of the graphics fuzz technique and how it works. And I now want to tell you a little bit about how this started and how it led to a startup company, which then Google acquired, before I tell you a bit about how we've been rolling it out at Google. Before I do that, does anyone have any questions regarding the technical material I presented so far? Okay, well, the project started around about October 2015. Like I mentioned, we were pretty inspired by that work from PLDI 2014, and we had a go at implementing something similar, but different, because we had to have a different take on it to overcome some of the specific difficulties of applying it in the world of graphics. And the first thing I want to say is, actually, with research, it can often be the case that a not terribly novel idea can go a long way. So this was something where, rather than thinking, I've dreamed up some clever idea of my own, I read this paper and thought, that's really cool. I wonder how hard it would be to try that in a different domain, and I wonder how well it would work. And that's what has then taken me on what's proved to be quite an interesting journey that's led to this startup company and successful acquisition by Google. So the point I want to make is, don't feel that you always need to be doing research that's supremely novel. If you can, and if you enjoy doing so, great. But also, there are many ways to have a fun time and dabble with interesting technologies by looking at what other people have done and seeing if you could apply it in another interesting domain. So in October of 2015, we started building an early prototype. And I vividly recall being on a train on the way back from London to the countryside where I live, and running like the first batch of tests from this tool on my laptop, and my laptop becoming completely unusable. And I tried to take a photo of it. It didn't come out very well, but on the right, you can maybe see this is Windows, and there's all kinds of crazy stuff going on the screen. And actually the laptop was flashing and flickering thanks to running some tests that had caused the driver to go into a pretty crazy state. And this was the first time I thought that I'd done some research that maybe could have some commercial potential, because it seemed really serious that by running just a small number of these fuzz tests, I could make my laptop become essentially unusable. I needed to restart it before it would get back into a reasonable state. I thought, this might be something that could have some serious impact. We published a short paper about the idea at the Metamorphic testing workshop in 2016. And that's only a 4-page paper, but actually, because the approach is very simple, I already told you about it in a few minutes, this short paper actually contains most of the main ideas behind the approach. Then we implemented it, really rigorously, and started to do some large-scale testing. And what we found was that we could find bugs in the drivers from all of the GPU vendors whose devices we tested. And this is another thing I wanted to say about research is that if you're doing something that isn't as novel conceptually, to some extent, when you're trying to get your work published, you can compensate for that by doing a really thorough evaluation. So if you've got a simple idea you're excited about and you can show that it works really, really well in practice, that can often overcome some grumbling from reviewers about how this is not the most novel thing they've seen this year, which you might get if you don't have such good practical results. So actually, the reason we found bugs across all these GPU vendors was not because we set out to do that for its own sake, but because we'd enjoyed working on this project. We wanted to publish it at a top conference, and we knew we could only do that if we had a big evaluation. So we tried it on all the devices we could get our hands on, and actually it turned out to work surprisingly well. And yeah, we figured that this would actually be of interest to many people in the graphics world, not just to PL academics. So we started blogging about the work via Medium and promoting it via Twitter. And going back to Ben's really nice talk from the last session, I think that you can get a lot more attention if you do some blogging and promotion on social media for your work than if you just write plain academic papers. I wouldn't necessarily recommend doing this for all of your work, but if you've done a piece of work that's a bit more practical than usual, that you think might have appeal to software developers in general beyond academia, then I think doing blogs and doing social media promotion can really get a lot more people to know about it. Then we started to really get the bug for doing something commercial. We thought, you know, this really could be something that the industry would find useful. There may be potential for a startup company. And it coincided with the UK government offering a scheme for academics interested in pursuing the commercial potential of a research idea. This iCure program provided funding for my former PhD student Paul and my then postdoc Hugh to travel the world and have dozens of meetings with a whole bunch of companies like Apple, Imagination, Intel, Google, Samsung, various others. And the clear message from engineers at those companies was, we like what you do, but for our management to buy your stuff, you would actually need to make yourself a problem, really make it be that your testing technique is showing the deficiencies in all of these GPU drivers that, that people around the world depend on. And if you can show that, then they will know, you know, this is a problem we have to fix, partly because we should fix it from an engineering point of view, but maybe more importantly from management, because it will be pretty bad looking if we don't take it seriously. Then we qualified for the next stage of this iCure program, which was called Cyber ASAP, the Academic Cybersecurity Startup Program. And that gave us some funding to build a product, like a really productized version of GraphicsFuzz that we could potentially sell to industry. Now, at this time, I really did not want to start a company. What I wanted to do was to see whether we could have this technology work really well and sell it via the university. So say, you know, it's here, we do some promotion of it. Companies can pay for it if they want it, but they get it via a license from the university. Maybe I would get some money thanks to that license, but more importantly for me, I would get to know from a curiosity point of view whether companies would buy this technology. For me, that was more important than particularly making money from the technology. And at the time, I was, you know, very happy in my academic career. My wife and I were expecting our third child. The idea of starting a company really didn't seem very appealing. However, I soon found that this idea of trying to license things to the university was pretty naive, because trying to sign non-disclosure agreements, NDAs, between universities and companies, at least at my university, but I think this is the case for many people, is a complete nightmare. Basically, the university contracts department, their job is to try to minimize risks to the university. And when they get one of these non-disclosure agreements, they want to look at it really carefully and start to try to negotiate it. But actually in industry, people sign non-disclosure agreements all the time. It's a very standard thing to do. The agreements are usually very simple. They don't carry that much force. You just need to sign them before you can get a conversation going. So what we found was we'd be talking to companies who were maybe interested in GraphicsFuzz, and they'd want to sign an NDA before we could talk further to see if they were potentially a bit more interested. And then weeks or months of negotiation with the university around the NDA would commence. And this would actually be kind of expensive for the company in terms of legal time, rather embarrassing for me, because the contact I had at the company would be getting kind of annoyed that they couldn't talk to us, or maybe annoyed that their legal department were having to be involved. And it just didn't really work at all. So actually, I first planned to start a company more so I could have a vehicle that would allow me to have a license to the technology from the university and allow me to take the personal risk of signing these very benign non-disclosure agreements, still with a view to talking to these companies to see if they would be interested in the technology and not particularly pushing it as a product. It took a while to actually negotiate all the details with Imperial Innovations to get a startup company going, partly because software license terms are genuinely hard and universities don't have that much experience in software licenses. In the meantime, we got our top paper about GraphicsFuzz at UPSLA, thanks to this big experimental evaluation. And we started to get quite serious about doing a company. I think we started to really get the bug to the point where we got a professional logo design, this logo for GraphicsFuzz you can see here. And having seen Ben's talk, I really regret that we didn't get stickers made. I think GraphicsFuzz stickers would have been a really great idea, maybe not too late. And then when we did launch the company, suddenly we thought, you know, if we're going to do this, let's do it properly. Let's try and really make our technology known. And we started to do some higher profile blogging and social media promotion of our product rather than our academic research. So we had a product, which was a test suite that we were trying to sell. And we had these blogs where we would do comparative studies of devices from with GPUs from different vendors, showing how well they performed on our test suite. In our blogs, we would show big tables of results where we would have like lots of different vendors and rows of test results. And these grids should, if everything was working, all have exactly the same image everywhere. But we would actually show that for various vendors, we would get memory corruption, or we would get link errors or compiler errors. And we finally finished spinning out the company. We started doing this promotion actually before the company was fully spun out because we got kind of impatient. And then relatively quickly, Google were interested and we were acquired by them in August 2018. So that's a bit of a whiz through the GraphicsFuzz journey from academic research project to startup company acquired by Google. And I suppose, you know, if anyone does their own startup, their experience will be completely unique. But the main things I would say from my experience is don't be afraid to give it a go. Don't necessarily think you've got to get all the I's dotted and T's crossed with your university before you can start trying to promote the technology. You know that these negotiations with the university will eventually work out. And if you can get people interested in the meantime, that can actually give you something you can use to try and speed up negotiations by pushing a bit harder. And again, don't feel like the idea you choose to commercialize has got to be your most intellectually interesting idea. I've worked on projects that I think have been much more intellectually stimulating than GraphicsFuzz, if not as fun to code, and if maybe they don't have as fun visual results. But I've worked on like invariant generation for formal verification, which was like very intellectually stimulating, but has way less potential for a commercial endeavor than something more simple and effective like GraphicsFuzz. Okay, and we kept the source code closed when we were doing this company, but as soon as we joined Google, we were able to open source it because Google really wanted to be able to use the technology for the good of the Android ecosystem, and have it be open source made more sense than trying to keep it closed. One thing I wanted to say regarding artifact evaluation is the Oops the 2017 paper coincided with us trying to spin our company out and having lots of IP discussions. And at that time, we just didn't feel too comfortable sharing the GraphicsFuzz source code with anyone, even artifact evaluation reviewers. So for that paper, we provided programs generated by GraphicsFuzz in lieu of actually providing access to the artifact. And I remember getting our artifact got rejected, and I think it was fair enough because we didn't give the reviewers the means to properly evaluate it. And one of their comments was, I think it's completely fair that they want to keep their tool private if they are thinking of commercializing it, but they can't get an artifact badge if they're going to do that. So yeah, that was our lack of artifact evaluation for GraphicsFuzz. But the tool is now open source and very easy to use. Okay, and what I'll talk about for a bit more is what we're doing now at Google, testing Android graphics drivers. Gaming on mobile devices is becoming a bigger deal as the years go by, and mobile graphics needs to be reliable. OpenGLES is the legacy API for graphics used by a lot of games now, but modern graphics is moving towards this newer API called Vulkan. So when we joined Google, our mission really was to make Vulkan graphics drivers as reliable as possible by finding bugs using our fuzzing techniques. But the trouble is that our technique, GraphicsFuzz, worked on the OpenGL shading language. It didn't work on Vulkan's SpearV shading language. But luckily, we were able to work around this by using a translation tool. What we do is we take an OpenGLES reference shader and we transform it using GraphicsFuzz to get one of these massively mutated variant shaders. And then we push both the reference and the variant through a front end called GLSlang that, among other things, is able to turn OpenGL shader programs into SpearV shader programs. So we do this for both the original shader and the variant shader. And then we can feed them to a Vulkan driver and get an image that we can compare as before. So by leveraging this cross-compilation tool, we were able to take our technology that works at the level of OpenGL and use it to test Vulkan drivers. This has some pros and cons. I mean, one pro is that it let us use the technology that we had brought with us to Google. Another pro is that GLSlang itself is an important tool that many people use, and we've been able to find some bugs in that tool and get them fixed. And also because many people are using GL slang, the kind of code that you get when you go from OpenGL to Vulkan via GL slang is important. That's a path that many people will be treading. So if we can find bugs in that pathway, then that's valuable. A clear downside, though, is that there are going to be many things that one can express in the Vulkan shading language that GL slang will never emit. So by feeding GL slang programs and depending on its translation, we're never going to test aspects of the Vulkan driver that GL slang is incapable of generating code for. So this has been a good way to get started, but there's a lot of scope for doing deeper work directly at the level of Vulkan. What we do when we find bugs is we use them to strengthen the Android compatibility test suite. This is a test suite that ships with every Android dessert release. So the Android versions traditionally have been named after desserts like marshmallow, nougat, Oreo pie, although they changed the numbers from Android. Would have been Android Q, they called it Android 10. And every dessert release has got an associated compatibility test suite. And if you want to make an Android phone, then if you want to be an official Android phone, you need to demonstrate that you pass this compatibility test suite. And new and more rigorous tests can be added to the compatibility test suite for future Android versions. And what we've been doing is we've been adding tests for bugs found by GraphicsFuzz continuously to the compatibility test suite for at first Android Q, then Android R that was recently released. And right now we're adding tests for the Android S compatibility test suite, which will be frozen sometime early 2021. And what this does is it ensures that the associated bugs will be fixed. Something that I hadn't appreciated until I joined Google was that there's a really long journey from a graphics driver being built at some company like ARM or Qualcomm, both of whom make quite widely deployed Android graphics drivers, and actually making out to an end user device. It can be the case that it can be months or even a year before a bug fix actually gets shipped to a user's phone via an over-the-air update, not because it couldn't be shipped sooner, but because doing an over-the-air update is quite high risk, and phone makers want to try to limit the extent to which these updates are needed. So if you put yourself in the shoes of a phone maker, you're kind of treading a fine line between wanting your phone to work as well as possible and be as reliable as possible and wanting to avoid the horrors of an update going wrong and maybe wanting to minimize the expense of doing an update. So if we just reported bugs, they might get fixed by driver makers and make it into new devices, but they might never get, those fixes might never get shipped to older devices. And by adding tests that expose the bugs to the compatibility test suite, we actually make it so that a device maker can't qualify for the next Android unless they ship drivers that fix these bugs. So it's a good forcing function, not for bugs to get fixed, but for those fixes to be rolled out to older devices, not just to new devices. Something completely different we've been doing at Google is actually using our metamorphic testing approach to find vulnerabilities in the Chrome web browser. The Chrome web browser is really widely used, and therefore loads of people are trying to attack it. And there's a project at Google called ClusterFuzz, which is a continuous approach to fuzzing the Chromium browser using a combination of sanitizers. So Chromium gets compiled with address sanitizer, memory sanitizer, thread sanitizer, and other tools like that, meaning that when you run the browser, various errors that might not be picked up by regular usage will be flagged as bugs. And then coverage-guided mutation-based fuzzing using libfuzzer, which is a bit like the AFL tool, to make mutations to inputs that you're feeding to the browser and see whether the mutated inputs can trigger security-related issues that these sanitizers pick up. Well, how does GraphicsFuzz fit into this? As I mentioned earlier in the talk, there's a technology called WebGL, OpenGL for the web, and that's implemented in Chrome. And WebGL vulnerabilities are therefore a concern. However, the Chrome security team don't really care about the kind of bugs we've been trying to find with GraphicsFuzz, wrong image bugs, where the compiler has silently generated wrong code. What they care about is exploitable vulnerabilities. So it's not like that they think wrong image bugs are okay. It's more that if they're not exploitable, they're not a major concern for Chrome. It would be nice to have them fixed, but it's not critical. But exploitable vulnerabilities are crucially important. They must be fixed. So how does metamorphic testing fit in here? Why couldn't we just do mutation-based fuzzing to take some WebGL workloads and apply random mutations that might make them completely invalid, but nevertheless, they might trigger exploitable vulnerabilities that could be fixed? Well, the way mutation-based fuzzing works is you take an input and you mutate it in a very straightforward manner that might not make it be valid anymore. So you have some initial test that goes all the way through the system you're testing. If it's a compiler, this test would go all the way through the parser, type checker, optimizer, and code generator. And if you had some other layered system under test, it would get all the way through these layers. And now you mutate it to get some input, T2. But that input is almost certainly invalid. It will almost certainly be rejected by the parser of your system under test. It may find an exploitable vulnerability in the parser, which is really good news because the parser is the first thing attackers will target. So if you can fix vulnerabilities in the parser, that's really good. But it's not very likely to find bugs in, say, the type checker, and it's extremely unlikely to find bugs in the optimizer, and even less so in the code generator, because it's really unlikely that a randomly mutated input will be valid enough to make it through to the back-end stages of the compiler or the deeper stages in some other layered system under test. In contrast with metamorphic testing, where we transform these inputs into equivalent inputs, an original valid input gets transformed into a mutated valid input. What that means is that we generate many, many tests, all of which get through to the back end of the compiler or to the later stages of whatever other layered system we're testing. This is great in that it may mean we can find exploitable vulnerabilities in deeper parts of the system. And it has the deficiency that because we only generate valid inputs, we won't find vulnerabilities in, for example, error handling code, because there shouldn't be any errors from these test cases. So we can find potentially deep vulnerabilities, but we won't find the kind of vulnerabilities that are triggered by malformed inputs. So in this sense, metamorphic testing can be useful for testing things like the Chrome web browser in a complementary fashion to more traditional coverage-guided mutation-based fuzzing approaches. And we've been using GraphicsFuzz with the ClusterFuzz team to find various WebGL vulnerabilities, like this one here that's briefly reported, a heap buffer overflow that was found by ASAN. And this one, when these bugs are fixed, after enough time has elapsed, after enough time that most users should have updated to a version of Chrome that isn't vulnerable anymore, these bugs get made public. And the final thing I wanted to say is that a nice property of this metamorphic testing approach is that the fuzzing tool actually tests itself. So when we run GraphicsFuzz and we look at results across a range of different platforms, I just made up the platforms here, but say we had a GPU from ARM, Intel, NVIDIA, and Qualcomm. If we find this magic program, variant 3, that triggers a bug in all of those drivers, then it will certainly be the case that this is actually a bug in GraphicsFuzz. GraphicsFuzz will have generated, due to a bug in the tool, a variant that is not equivalent to the original. And thus we get the same, what looks like a bad image, but it's actually the correct image for that variant across all of these different drivers. So if you want to know who fuzzes the fuzzer, well, the fuzzer fuzzes itself. So in summary, GraphicsFuzz is a metamorphic testing approach for graphics shader compilers. It generates families of equivalent shaders using semantics preserving transformations. And we've been using this for several years to find bugs in many GPU drivers, but it led to a startup company that Google acquired. And we're now mainly using it to find bugs in Android Vulkan drivers. When we find tests that expose bugs, we can add those to the Vulkan compatibility test suite to defend against them returning, and also to force phone makers to roll out fixes for those bugs when they update older devices. And somewhat surprisingly, GraphicsFuzz, even though it wasn't designed for this purpose, can find WebGL vulnerabilities due to the property that valid inputs generated by metamorphic testing can go deep in ways that typically invalid inputs generated by more naive mutations can't. As I mentioned, these approaches are complementary to one another. So what about the future for this project? Like I mentioned, testing via cross-compilation, where we fuzz at the level of one language and cross-compile into another, has some advantages, but it also has limitations in that we can't get good coverage of aspects of that lower level language that the cross compiler can't target. So we're right now working on direct fuzzing for Vulkan. We're always looking at ways to make the approach more automatic so that there's less and less manual effort involved in setting off fuzzing, monitoring it, triaging bug reports, and making these compatibility tests. And something we'd like to do at some point is look at fuzzing, not just at the level of the shader programs given to the shader compiler, but at the level of the whole command stream that gets fed to these graphics APIs to find vulnerabilities elsewhere in the graphics stack. Okay, thanks very much for your attention, and I'd be delighted to take any questions.
Thank you, Alistair. That was great. Okay, I can open up the floor for questions. I could even, I'm dying to ask a few myself too, but making sure that I've got, if anyone wants to hit the chat. But in the meantime, Alistair, I'm just wondering, you know, many things, but your journey is maybe the modern journey of the academic. Like I'm not sure, but it does seem like there's so many exciting things in what happened and twists and turns with NDAs. And so I'm wondering if you could just comment for all of us, you know, older academics or the ones that are just graduating soon here in the doctoral symposium, you know, from your takeaways, is this something that you would really, it sounds like you're recommending it in a way, like this is a fun part of the journey? Or would you say, well, look, it happened and it was really interesting, but I'm not sure that I recommend it.
Well, actually, what I think is the wonderful thing about academia is that there are so many ways to be an academic. And I truly think that's something that you maybe don't appreciate when you are an academic. But, you know, part of what's been interesting for me about, because I'm joint between Imperial and Google now, and it's been interesting doing both. And I think, you know, I've got a great taste for the industrial side of things, but also it's maybe appreciates, you know, some of the things in academia that maybe I didn't appreciate as much. So two parts to your question, two parts to the answer. One is, I wouldn't recommend it to everyone. I find it really fun. It was kind of an accident, as I tried to illustrate when I went through the, you know, the story. But I think rather than saying you should try doing a startup, I would say, if you are an academic, especially if you have, once you manage to get a permanent position, and in the UK, we don't have to go through tenure, we get like these nice permanent positions from, you know, from the day you get it. Or yeah, once you've got tenure, say, if you're in a country that has that, really think about all the things you could do, and don't try and do all of them, but try and do the ones that excite you the most. So if you want to write a book, do that. If you want to become an LLVM wizard, go do that. If you want to do a startup company, go do that. Do research, do a really good job of your teaching, but do explore the opportunities that you can do as an academic that most people in most jobs can't do. I guess regarding doing a company, it's quite stressful. So it's been really fun doing it, but life's a big balance and trade-off. And yeah, it's been kind of energy sapping being an academic, doing the company, doing the negotiations to sell a company, which are time consuming and non-trivial, as well as, you know, family commitments, et cetera, et cetera. So I wouldn't say it's something that you can just kind of, I guess I did do it in my spare time, but I had to sacrifice many other things to do it in my spare time.
Right.
Yeah.
That's great. Thank you very much. And I think Emma's got a question.
Yeah, thank you so much for the talk. It's very interesting. And having been at Google for a number of years, I'm kind of curious how your day-to-day, you know, how do you balance these two roles that you have? Do you still teach, but you go to the office in London or some other place and sort of code some days, or what does it look like?
Well, at the moment, I just sit in this room all the time.
Oh, well, of course.
But what I've been doing before COVID was 1 day a week for Imperial, but rather than doing it like rigorously on a specific day, spreading the time through the week. So I got some fixed time. I go there to see students. My teaching is compressed into a particular part of the year. So during that part of the year, I'd go there more often. And then the rest of the time, I would commute to London. So I typically use all my commute time to kind of get on top of my academic work and work on papers and work on teaching materials, etc. Yeah.
Great. And we have another question, Arnav.
Thanks for the nice talk. It was really interesting. And actually, I was interested in it because I worked with metamorphic testing before, and yeah,
cool.
paper on the testing, using metamorphic testing to test basically machine learning implementation. So basically, my question is a bit detailed. I wanted to ask you that the metamorphic relationship that you have considered here. So how do you decide that? Is there any particular way of deciding, or is there standard metamorphic relations in testing compilers, or yeah, how you decide which are the metamorphic relations you should consider?
Thanks for the question. The top level metamorphic relation is simply that on equivalent programs, the compiler should generate executables that yield the same output. So that's the kind of top level metamorphic relation. And then there's, I suppose, an infinite set of things you could do to make equivalent programs. So I suppose maybe your question is more about how do we decide which transformations to apply?
Yeah.
Yeah. Well, there are three ways. One is inspiration from previous work. So that PLDI 2014 paper I mentioned that inspired getting into all this stuff made the point that control flow related bugs were quite common in compilers. So one of the first things we tried in our approach was things like injecting some code that would be unreachable and then having return statements in that code or breaks out of loops from that code. So complicating the control flow graph of a function in ways that make it be radically different from an optimizing compiler's point of view, but don't change the semantics. So inspiration from prior work is one way. The other thing is talking to compiler developers. So when we joined Google, we got access to a lot more people who work in the world of Vulkan and OpenGL, and they would say things to us. Oh, I remember a bug that involved blah, blah, and blah. And we'd think, okay, yeah, we could implement a transformation that involves blah, blah, and blah. Okay, but cool. Probably the biggest deciding factor is how easy these transformations are to implement. So in a tool, you can look at a language specification or just have an idea and think, oh, it would be so easy to just swap the order in which functions appear in a file. Very unlikely to trigger a bug, but trivial to implement. Let's just add that to the tool, right? So anything that you can just throw into the tool because it's really easy to implement, you may as well throw in. And then you have things that are a bit more challenging to implement that involve a bit of nice, fun compiler analysis, and you can do them. And then you have things that you implement that are as hard as building like a proper parser and an optimizing compiler. And usually then they're not worth implementing because you don't know in advance whether they'll find anything. It's sure that they're going to be buggy and you're going to spend a lot of time thinking you found driver bugs, but actually turns out there's a bug in the testing tool. So yeah, combination of prior work, suggestions from people in the know, and just having ideas and deciding which ones are just no-brainers to implement versus which ones would probably be a lot more work.
Cool. Thanks.
And I think we have some advice from Ben coming in now too.
No, not advice. Actually, a real question. Alistair, thank you for a very motivating and inspiring talk. I took a few notes on the side, actually. I was asking myself, I never thought of fuzzing graphics drivers, and it's a brilliant idea. If you could look 5 years into the future, what would be the next thing we apply fuzzing to with a similar impact? What do you think?
Well, I'm not telling you because that's what my next startup company is going to be based on. No, I'm
Damn.
I don't have a particularly good answer to that. I think there's a lot of scope for trying to apply fuzzing to machine learning because, and I think people are doing this already, looking for, in adversarial machine learning. I don't know too much about it, right? But like, I think there's a lot of scope for saying, we've got this machine learned, this machine learning system that can recognize things of this form. Why don't we fuzz things into a whole load of forms that should be, equivalently easy to recognize and make sure it can recognize them? That would be like I think people are already doing this kind of thing. A few years ago, I was thinking, maybe I should try and get into that too, but I haven't. I think that media processing. So if you think about like web browsers, more and more they are running rich content. And I think if you can fuzz that content and find vulnerabilities in the kind of media players that everyone is using all the time. That could be pretty interesting. Again, people are working on that, but I wonder whether this validity preserving mutation is something that people have not looked at, right? So just taking a video file and mangling it, yeah, people are doing that, but like looking actually at what the video format is and trying to do interesting, valid transformations on that format, and then maybe mangling them a little bit, that could be interesting. But frankly, I like want to work on something different. You know, I mean, I want to see GraphicsFuzz through, but part of me is longing to get back into formal verification and more theoretical work and prove some theorems, and maybe no one will use my stuff, but it's like intellectually very satisfying. And going back to what I said about academia, I think it's wonderful that in academia, if you have a secure position, you have the freedom to go and explore these things for their own sake.
Very interesting. Are there any other Zoom questions coming in for Alistair? Maybe I have one quick last one, and then maybe we could take a little break, and then we'll do the roundup. But just curious, Alistair, about the students that you're working with. Do you get a lot of students that show up and go like, "Okay, great, I want to work on this," because you're so well known for it, or are you still getting a lot of students that kind of are coming in for the more traditional formal verification supervision that you?
Actually. The thing that was hardest for me about joining Google was trying to not let my students down. So as soon as I was able to tell them what the plan was, I worked to kind of come up with good co-supervision relationships with some colleagues so that they would have people who were available more than I was, and very specifically not to take on any more students. So I've been letting my academic pipeline flush a bit. I'm about now at the point where I probably would like to take on some more people, but at first, I think it was like hard for me and hard for my students, but hard for me to cope with what was a lot of work for me, and hard for them to cope with not having nearly as much supervision. So yeah, I haven't had, but actually I've always found it hard to attract students, always. And I think even at a university like Imperial that has a pretty good reputation, it's difficult to get good students, especially in programming languages, which is, I think, you've got to kind of get the PL bug. It's not easy. It's like one of the harder areas of computer science. And once you understand how amazing it is, you don't want to do anything else. But a lot of people are into machine learning these days, or in London, there are all kinds of very interesting industrial opportunities that people can take. So yeah, attracting students has never been something I've found easy. I always feel very privileged when a good student does approach me and I'm able to attract them.
Exciting. And I think we have Doug with a question.
Yeah, it's a half question, half comment for Ali. So I think one commonality is that if you're in PL/system/SE, something you do in your life will be a little disruptive. It'll be overhyped, or it'll involve working with companies, or it'll be something that's just not classically academic. And we don't prepare students whatsoever for that to happen unless they happen to be working with somebody who is in, one of those categories. I don't have any good suggestions, but about what we could do. But any thoughts, Ali?
It's difficult because I agree with you, but it's not like we can predict what this disruptive thing will be necessarily.
Yeah.
What I think, the only thing that springs to mind is if you do work in a practical area, I think that engaging with industry via, say, reporting bugs or patches to open source software, or, unless you've got a reason not to, like we did initially with GraphicsFuzz, making your stuff open source and trying to then collaborate with people who want to contribute to your project. I think that open source is quite a good way to cross the academia industry gap. And I think that's the only idea I have, really, just making sure that people are pretty confident doing somewhat professional software development using, which I think most PhD students are these days, but I certainly wasn't when I did my PhD, using a lot of these platforms and frameworks and being used to code review and all that kind of thing.
Thanks.
But yeah, I don't feel that's a very satisfactory answer. So no, I don't think I've got any good ideas there.
Better than I would have done.
Well, Doug, I was going to say, do you have a comment from your own experience?
No, it's, you know, what I asked was sort of a generalization across our experiences is that it's so hard to predict that, you know, you're doing what you do and suddenly they want you speaking in front of 10,000 people, or or some company wants to talk to you, or you get called up by the New York Times about the political intrigue of corporate warfare associated with what you're doing. Yeah, I lived through all those things. Yeah, nothing prepares you for that. But I think people in this, you know, ill-defined realm of PL systems, SE, we're prone to it. You know, it's inevitable. You're working in these kinds of areas. Somebody's going to be paying attention someday. And if you could guess what it was, well, you'd probably be off doing it instead.
Exactly.